In section 2.4, we will talk about continuity. By definition, a function is continuous if you can sketch the function without lifting your pen, pencil, digital utensil, whatever you're using. If you cannot sketch the function without lifting up your pencil or pen or digital pen, then it has some kind of a discontinuity and is not a continuous function. As you can see, the first function is continuous because I can sketch it in one constant motion, whereas the second function, here it stops and it continues again at about 2.4, the y value of 2.4. So this is a discontinuous function because I can't sketch this function without lifting up my digital pen. Okay, now we're going to talk about the formal definition of continuity at a point. So let's first go over the definitions and we'll go over some examples. So continuity at a particular point is given by three requirements. A function f is continuous at a point C if the following three conditions are met. So number one, f of c is defined. And I'm going to go through like examples of what each of these means and doesn't mean. So here's an example of when f of c is defined. So let's say I have a curve like this, and I'm looking at x equals to 1. Okay, that's my c value. So f of 1 in this case is defined because that point exists on the graph. So f of 1 is defined. Okay, now let me show you an example of where it is not defined. If I sketch another curve, but at x equals to 1, we have a hole. A hole means that the function has no value at that point. So in this case, it is not defined. Okay, second one is a limit of f of x exists. So we know that a limit exists if both from the right and left we approach the same value. So in this second example that I gave you, where we have a hole at x equals to 1, even though the function isn't defined, a limit still exists. Because remember, a limit doesn't mean the function has to be defined at that point. It just means that from positive and negative infinity, or from the left and right, we just have to approach the same value. So from the left and right, the function is going to approach the same value, so the limit exists. Now let me give you an example of where the limit does not exist. If you have a case like this, where from the left, we're approaching one value, and then from the right, we're approaching a different value, then the limit doesn't exist. Because coming from negative infinity, we're approaching one y value. Oops, sorry. Coming from negative infinity, we're approaching one y value, but coming from positive infinity, we're approaching another y value. So in this case, the limit does not exist. So the first two conditions that have to be met is that f of c has to be defined, the limit of f of x as x approaches c exists, and then finally, the limit of f of x as x approaches c has to equal to f of c. All right, so the limit of f of x as x approaches c has to equal to f of c. So this one might be a little bit more tricky to understand, but let me try to explain that to you. So once again, we have a curve like this. We have x equals to 1. And let's say this is y equals to 2. So first off, the limit of f of x as x approaches 1 is going to be 2, because from both the left and the right, it's approaching a y value of 2. So this here equals to 2. Now f of c, in this case, it would equal to f of 1. F of 1 is also equal to 2. So because of that, the condition is met and the function is continuous. Okay, but if you take a look at another example, so let's say we have a case like this where we have a hole here, and then we have this graph. So once again, let's use x equals 1, y equals 2, but then I'm going to actually introduce another point. A hole means the function is undefined at x equals to 1 at that y value, but let's say this is a y value of 4. In that case, the value of the function when x equals to 1 is equal to 4. So now the limit of f of x as we approach x equals 1 from the left and right is actually equal to 2. And the reason is because if you look at it from positive and negative infinity, we're going to have a limit of 2 because that's what the function approaches. Okay, from the left and the right, it's going to approach 2. So the limit is going to be 2. However, if we look at f of 1, so the value of the function when x equals to 1, that's equal to 4. A closed circle is the value of the function at x equals to 1. So because the limit is 2 and because the function has a value of 4, this condition is not met. So let's take a look at some examples. Well, before that, I'm sorry, we have different types of discontinuity. So the first type of discontinuity is called a jump discontinuity, which means a function is going to basically jump from one y value to the next at a particular x value, and the limit doesn't exist. That's called a non-removable discontinuity. A removable discontinuity is where, let's say we have a function, and we have a limit of a function is one value, but then the value of the function is a different value, the limit and the value are different. This is a removable discontinuity, and it's removable because let's say we just fill this in and make the function defined at that point, then the limit and the value of the function would be the same. So that's called a removable discontinuity. And then the third one is called an infinite discontinuity because from positive infinity, the limit is infinity. From negative infinity, the limit is negative infinity. So the limit doesn't exist since from the left and right, it's approaches two different values. So therefore, this is called an infinite discontinuity. So the first example says we're given a graph. Select all the statements below that you agree with. So let's go one by one. Is f of 2 defined? So in other words, is there a closed circle at f of 2? And yes, f of 2 is defined. And in fact, the value of f of 2 is equal to 2. So we're going to check that off. Number 2, it says that the limit of f of x as x approaches 2 exists. So for the limit to exist, we're looking at x equals to 2, and we're going to follow the graph from negative and positive infinity. So coming from negative infinity, so here, the graph is going to approach a value of 3. Coming from positive infinity, so from here, the graph is also going to approach a value of 3. So the limit of f of x does exist, and it equals to 3. Now, is the limit of f of x as x approaches 2 the same thing as f of 2? No, since the limit of f of x as x approaches 2 is 3, and then the f of 2 is defined as 2, these two are not equal. Therefore, we have something called a jump discontinuity, which is going to be this case. We have a jump discontinuity. And because we have a jump discontinuity, we're going to say that the function is not continuous at x equals to 2. And we can even see that, right? There's no way to sketch this curve without lifting our pencil or pen or digital utensil. So it is not continuous. Here's another one. So let's take a look at the first case. Is f of 2 defined? So at f of 2, does a y value exist? Yes, a y value does exist, and that y value is equal to 4. So that's true. Does a limit exist? So coming from the left, so coming from negative infinity, the left of x equals 2, the limit is 4. And then coming from the right, so coming from positive infinity, the limit is 3. And so because the limits are different, the function does not exist. Or sorry, the function is not continuous at x equals 2 because the limit does not exist. Okay, let me rephrase that. The limit doesn't exist, therefore the function is not continuous. All right, what about this one? Let's say, which of the following rules is first violated at x equals to 2? So let's go one by one. Is f of a defined? So we're looking at x equals to 2. Now, if x equals 2 was defined, we would either have a continuous graph or a solid circle. And we don't have either of those, so f of a is not defined. And if it's not defined, it cannot be continuous. Okay, next one, it says, select all the statements with which you agree. First one, we have f of negative 3 is defined. So first off, we have a piecewise function. And if x is less than negative 3, we use the first formula. If x is greater than negative 3, we use the second formula. If x equals to exactly negative 3, we use the third formula. So f of negative 3, it means we want to find the value of the function at exactly x equals to negative 3. So when x equals to negative 3, the function has a value of 2. So yes, it is defined. Next, does the limit of f of x exist as x approaches negative 3? So for a limit to exist, if this is your x value of negative 3, then coming from the left, so values of x that are smaller, and coming from the right, so values of x that are larger than negative 3, we should approach the same exact value. So we're going to look at the function coming from the left, so values smaller than negative 3, and from the right, values larger than negative 3. So what happens if we take a look at the function when x equals to negative 3 coming from the right, or from positive infinity? So if x is greater than negative 3, we're going to be using this formula. So I'm going to plug in, the formula is radical x plus 84. I plug in negative 3. That gives me radical 81, which equals to 9. So coming from the right, the limit is equal to 9. Now, what if we come from the left? So if we have values that are less than negative 3, we use the formula 5x plus 24. And remember, x is negative 3. So we have 5 times negative 3 plus 24, which also gives us 9. So this is good, because as x approaches negative 3 from the left and from the right, we have the exact same y value, which is x equals to 9. So the second condition is met. What about the third condition? Is the limit as x approaches negative 3 of f of x equal to f of negative 3? So the limit as x approaches negative 3 is 9, but f of negative 3 is 2. Since 2 is not equal to 9, the function is not continuous at x equal to negative 3. We're going to get a jump discontinuity. All right, next it says, let f of x be a function. So now we're told that it is continuous everywhere. Then what does m have to be? Well, if the function is continuous everywhere, then as x approaches, so we're looking at a value of negative 4. If it was continuous, then as x approaches negative 1 from the left and from the right, they must equal to the same value. So for a function to be continuous, the limit of f of x at x equal to negative 4 must exist, which means from both the left and the right, f of x must approach the same value at x equal to negative 4. So we're going to say that mx minus 9, the left side, has to equal to x squared plus 5x minus 5, the right side, when x equals to negative 4. Now, since we know x equals to negative 4, we can plug this in. So if I plug in x equal to negative 4, we're going to replace the x value on the left with negative 4, and then each of these x values with negative 4. So we're going to get m times negative 4, which is negative 4m minus 9. And then if I simplify this, I get 16 minus 20 minus 5. That gives me a negative 9. And if I solve that, I get m equal to 0, which is the value of m that satisfies the continuity requirement. So for this problem, we're going to set the two equal to each other because the limit from the left and the right must be equal. And then we're just going to plug in x equal to negative 4 in order to solve for m. Lastly, the intermediate value theorem says that if f is continuous on an interval from a to b in case any number between a and b, then there's at least one number in the interval ab such that f of c equals to k. So basically what it means is, let's say that you have f of x, a continuous function, and f of negative 4 is negative 10. So you're below the x-axis. So you're like down there somewhere. And then f of 0 is positive 10. So you're up there somewhere. At some point, to go from a negative to a positive, the graph must have crossed the x-axis. So suppose that f of x is a function with f of negative 4 equal to negative 10, which is the following statement. Now this is kind of a trick question because we aren't told that the function is continuous. And that's one of the requirements for the intermediate value theorem. So this is going to be sometimes true and sometimes false because we're not told whether f of x is continuous or not.